So we have to find out the value of V, this voltage, in this Isaac physics question. And what we have is a simple long piece of some type of wire, probably quite thick, with a uniform resistance per unit length, which has been broken down into two lengths, L1 and L2, and then labelled X, S and Y, as you can see. And the point S, the flying lead here, is moved backwards and forwards until the ammeter reading is exactly 0. And then using that fact, we should be able to work out the value of V. Now, I always like to draw these things out as a proper circuit diagram. I know you could say this is too, but I just find this is, it helps me to think as I draw it out about what I actually need to be doing. So first of all then, let's see if we can get some values of voltage and values of current through the wire, R1, R2 or L1, L2, depending on how you want to think of it. So first of all then, we can say that the voltage between X and S is going to be equal to V1. So we'll label it here, and we can say that because the two ends of the power supply quite literally go to the resistor. So we've got the voltage XS equals to V1. What's the voltage from one end of the wire to the other, X, Y? Well, that simply equals a V for the same reason. Those 2 points are connected back to the cell. And what about the current? Well, let's consider the current that's flowing along this direction here. If we know that the current here equals 0, which the question does say, then that means that the current through R1 and through R2 is going to be the same. So we could write that as I in the strip XS, the first bit, is equal to I in the second bit, or through the whole thing, depending on how we want to write it. So we could do XY, or we could even say I equals SY, ISY, and we're going to call all of these I. And this all comes out of the fact the current is 0 down there. Okay, next step then is to remember everybody's favourite electrical formula, V equals IR. What we're going to do is get values for R1 and R2. So let's do that next. So R1 is going to be the voltage across R1, which we've just said is V1, divided by I. And then we're going to say, what is the resistance of R2? Well, the voltage across R2 is going to be big V, take away V1. That's the voltage across it, again, divided by the same current. Now, if we rearrange these two to make I the subject, we get I equals V1 over R1 and I equals V minus V1 over R2. And now we can set those two equal and do a little bit of algebra. So the next step then is to set, as I said, set these two equal. So we then get that V1 over R1 equals V minus V1 over R2. So our next job then is just to rearrange this and get V equals to something. So that implies then we bring the resistances up on top. V1 R2 equals R1V minus RV1, and it's R1 of course. Yes, that's correct. R1V minus R1V1. So the next thing that we want to do is get this V on its own. So now it's just a bit of algebra really. So let's rearrange to get V. So I did V1 R2 plus R1 V1 equals R1 V. Take out the common V1, so we've got V1 R1 plus R2 divided by R1 equals V. Now because the wire between X, S and Y that they've labelled L1 and L2 has a constant resistance along its length per unit length, we can therefore say that this ratio here, because this is just the ratio of the total resistance divided by R1, can be rewritten as L1 plus L2 over L1. And therefore the whole thing becomes, just need a little bit more space, the whole thing simplifies down to the V that we're interested in equals V1 times L1 plus L2 over L1. Bob's your uncle, as they say.